All right, let's talk about something that sounds impossible. Imagine you've built an AI model to diagnose a pretty serious disease. The results come in and boom, it's 97% accurate. I mean, that sounds amazing, right? Practically perfect. But what if I told you that this brilliant model was actually a complete, total failure?
It just doesn't seem to add up, does it? How can something be so right and at the same time it's so fundamentally wrong? And no, this isn't some kind of trick question. It's actually one of the most important and honestly one of the most overlooked challenges in all of machine learning. I mean, just look at that number, 97%. In just about any other situation, that's an A+. It's the kind of number that makes headlines, it gets you funding, but in this case, it's a mask. It's hiding a really critical flaw.
And there it is. That's the whole trick. If your data is lopsided, a lazy AI can get a fantastic score by just guessing the most common answer every single time. This is exactly what a 2020 study on diabetes found. A model can look like a genius on paper while completely failing at its one single crucial job, finding the people who are actually sick.
This right here is the core problem, and it's got a name: imbalanced data. And you see it everywhere in the real world. Think fraud detection, finding rare diseases, spotting defects on an assembly line. The very thing you're searching for is by its nature pretty rare. In that Zada study that we're looking at, the imbalance wasn't even that crazy, but it was more than enough to completely fool the standard algorithms.
But, this isn't some brand new problem. Actually, this story of how researchers figured out how to fight back against this illusion is a fantastic example of scientific discovery. And it all started with one person's incredibly frustrating moment of failure. This quote is just perfect. Nitesh Chawla, the guy who invented the technique we're about to get into, he had the exact same 97% failure moment we just talked about. He was a grad student working with mammography data, got this amazing 97% accuracy score, and then realized his model was actually worse than just guessing not cancer over and over again. And that moment of frustration, that was the spark for a truly brilliant idea.
Now, the simplest solution you might think of is, hey, if you only have 3 sick patients, why not just make like 30 copies of them? The problem is that leads to something called overfitting. The model doesn't learn the general pattern of what sickness looks like. It just memorizes the exact faces of those 3 specific patients, which you can imagine is not very helpful for diagnosing anyone new.
So Chawla came up with a much smarter approach called SMOTE. Instead of just copying the data, it creates new data. The way it works is actually pretty simple but really powerful. First, the algorithm picks a sick patient from the data. Then, it finds a few other sick patients that are similar to it. And finally, and this is the clever part, it creates a brand new, totally synthetic patient by picking a random spot on the line between them. The paint analogy is perfect. You're mixing red and blue to get purple. You're not just reusing the original colors, you're making something new from them. And this gives the model way more varied examples to learn from.
Okay, so we've got this really elegant theory for creating synthetic data points. But does this clever little trick actually make a difference back in the real world? With real patients? Let's jump back to that diabetes study and see what happened.
I mean, this is the million-dollar question, right? It's one thing to have a cool-sounding algorithm. It's something else entirely for it to actually have a real impact. And to answer this, we need to stop looking at that misleading accuracy number and start looking at the metric that truly matters in a case like this.
And that metric is called recall. So let's just forget about overall accuracy for a second. Recall asks one simple, vital question. Of all the people who were actually sick, what percentage did our model manage to find? In medicine, this is everything. You would much rather have a few false alarms than miss a single person who really needs help. And this table just lays the problem bare. Before they used SMOTE, the models had these pretty decent-looking accuracy scores. But just look at the recall numbers. The naive Bayes model was finding less than 10% of the diabetic patients. That means it was missing over 90% of them. Even the best model was failing to find almost half of them. This is the 97% illusion, live and in color.
Okay, now for the magic. Look what happens after applying SMOTE. The accuracy numbers, they barely move. Some even go down a tiny bit. But who cares? Look at the recall. Naive Bayes jumps from finding just 9% of sick patients to over 76%. The decision tree goes from 57% to an incredible 85%. By creating smarter, synthetic data, the models finally learned what diabetes actually looks like, and now they can find the people who really need help.
So, problem solved, right? SMOTE is the magic bullet we can all pack up and go home. Well, not so fast.
Like with any powerful new tool, researchers pretty quickly discovered there was a hidden vulnerability.
See, the very thing that makes Smote so smart is also its potential weak spot. It trusts the data you give it. It assumes that if a medical record says a patient is sick, then they're sick. But what if there was a typo in that record? What if a patient was misdiagnosed in the first place? This is what we call noise in the data. And this is where it gets a little dangerous. If Smote takes a genuinely sick patient and mixes it with a mislabeled healthy patient, well, the new synthetic patient it creates is just going to be a confusing mess. It's like making a photocopy of a blurry photo. You just end up with more blurry photos. You're actively polluting your data set with garbage, and you risk teaching your algorithm all the wrong patterns.
But of course, a challenge like this didn't stop researchers, it just pushed them to be even more clever. It led to the next step in the evolution of this idea. How do you make this amazing technique for creating synthetic data more robust, more reliable, especially when you know the real world is messy and full of noise?
The solution, it turned out, was to build a protective layer around Smote. The original version is fantastic at fixing the imbalance, but it's vulnerable to that noisy data. So the next generation, with the very catchy name FRIPS Smote, FRBPS, adds a crucial new step, data cleaning.
So basically, they created this robust three-step process. Think of it like a professional cleaning crew for your data. First, an algorithm comes in and does a pre-clean, removing any noisy or just plain weird data points from your original set. Then, Smote does its thing, but now it's working with much cleaner, higher quality data. And finally, the cleaning crew comes back one last time for a post-clean to polish up the final data set and remove any odd synthetic points that might have been created. It's Smote, but with guardrails.
So what's the big picture here? What are the key things to take away from all this? First, and most importantly, never, ever blindly trust a high accuracy score. You always have to dig deeper and ask, is this really the right way to measure success for this specific problem? Second, remember the big idea behind Smote. Intelligently creating new data is often way more powerful than just copying the data you already have. And finally, this whole story just goes to show that building reliable AI isn't about finding one magic algorithm. It's a continuous process of finding a flaw and then engineering an even smarter solution to fix it.
Which really just leaves us with one last big question. We've uncovered the accuracy illusion, we've seen the danger of noisy data, but as we start using AI in more and more critical parts of our lives, from reading our medical scans to deciding who gets a loan, what other hidden flaws, what other silent failures are we still missing? What's the next 97% illusion that we haven't even thought to look for yet?